Welcome back to the course on architectural design of ICs. So, we are seeing in the last class we are discussing about the Booth's algorithm for reducing the partial products. Okay. So, that means what I said that if I consider more number of bits or the word length is more for multiplication operation. So, at that time in general multiplication the depth is basically also it becomes more. Means what? If I consider n into n bit number of multiplication, so at that time what happens, the depth is also of, that means this n bit. If n is 16, so that means 16 stage of addition operation, 16 stage of operation, that means addition operation I require. Okay. If n is, let us consider 32, so at that time 32 stage of addition operation I require to perform for the final computation of the multiplication operation. So, that is why what we have done, we have that means used this Booth's recoding technique to further reduce the number of this stage of this chain addition operation. Okay. So, how we have reduced? Based on this particular algorithm, that means this based on this particular equation, which is nothing but this, if I choose that Radix-4 Booths algorithm. So, at that time the corresponding recording bit that has been selected as -2 into b I plus 1 plus b 0 or b I into b I minus 1. Okay. So, this is for Radix-4, and based on that now, so if I, that means I will get what, 3 bit combination for 0 0 0 for 0 0 1. So, this is b 2, this is b 1 and this is b 0. So, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. Okay. So, now the thing is that, so for this 0 0 0, so for this particular case if I consider, so at that time for 0 0 0, what is that? 0 plus 0. So, this is 0. Okay. And for 0 0 1, that is 0 plus 0 plus 1. Okay. This is 1. For 0 1 plus 0, that is 1. For this particular case, that is 0 plus 1 plus 1, that is equals to 2. Then again for this is -2 plus 0 plus 0, that is equals to -2. Then again for this particular case, that is -2 plus 0 plus 1, that is equals to -1. Then for this -2 plus 1 plus 0, that is equals to -1. Okay. Then again for this case -2 plus 1 plus 1, that is equals to 0. Okay. So, this is the operation which I need if I do this corresponding decoding. Now, we have taken one example, and at that time we have seen at the very last, suppose this, now I need to add a into b, correct. So, b if I consider, so at that time very end of b I have to add 1 0 and then I have to consider the corresponding 3 bit. Suppose if b is known as, let us consider that is b 3, b 2, b 1, b 0, 4 I have to consider another 0 over here. Then at the very first I will consider these 3 combination and then there will be one overlap of this. Okay. So, whenever I am having, initially I am having what, how many times? I am having 4 partial product set. Okay, 4 partial product set. That means I need 4 stage of addition addition operation. But in this, if I use Booth's recording, Radix-4 Booths recording, so at that time PP1 for this particular case and PP2 for this particular case. So at that time I need only two partial product sites. So that means here I need only two stage of addition operation. So that means two addition operation I have reduced by using this recording technique. Okay. So this is the beauty of this Booth's multiplication, how we can reduce the delay by 50%. Now in case of what that means, suppose for if the n is 64, so at that time what I need 64 stages of addition, right. If I use Radix-4, still I need 32 stages of addition operation, still it is more. So at the time, can I increase this radix so that I can reduce these terms? So if I want to increase the radix, so at that time what will be its decoding table? So if I just, if you remember, based on one particular equation I have, that means come to what will be the operation. So here also if I want to change the corresponding radix, so suppose radix 8, so at that time what will happen? It will be this, at the time while will be what? This will be the position, okay. And here the corresponding value will be something like this, okay. So that means here in the earlier case what was there? That means that was in this particular position, that is -1. Here 2 to the power 2 will be the minus case, okay. So that means now considering these things, so there will be 0 0 0, 0 0 0 1, 0 0 1 0, 0 0 1 1, 0 1 0 0, 0 1 0 1, something like this. So for this case it will be 0, for this case 1, for this case again 1, for this case this is 2, for this case this is 2, for this case this is 3, for 0 1 1 0, again this is 3, then for 0 1 1 1, this is total 4, then again for 1 0 0 0, this is -4. So something like this I will get. So that means now these partial products I have to generate from the beginning, okay. So now again whenever we will consider this this B, at that time what will happen? Suppose if I consider, that means B 8 bit, okay, B 5, B 4, B 3, B 2, B 1, B 0. So initially I have to put 0 over here, okay. So if I consider radix 3, at the time what will be the sets? 1, then 2, then 3, then 4. So that means this is PP1, this is PP2, this is PP3, this is PP4. But in case of, this is case of radix 2. In case of radix 4, what will happen? I have to consider 4 bit. So at that time what will happen? this is PP1, and again this will be starting from this, not actually not this, at the time I have to add 2 0 over here. So, this will be something like this, means what? If I just rewrite, so B7, B6, B5, B4, B3, B2, B1, B0 along with this 2 0, at the time it will be something like this. This is PP1, then this is PP2, then okay. So, something like this I can do. So, more the number of bits we consider, that means if we consider 64 bit multiplication or 32 bit multiplication. So, at that time I need to use, this is for Radix-4, this is for Radix-8. Okay. So, more the number of Radix I can choose for Booths decoding. But the thing is that whenever as in the previous case, so I will get 16 combination and I need to generate these partial products from the beginning based on the corresponding set. So, that means more the number here I consider, more the number of partial products I need to generate, or this decoder size will be also more. Okay. So, we have to be, that means choose this number of radix in a judicious way, so that I am getting the benefit in terms of this delay, that means stage reduction whenever we are considering or hiring the radix using this Booths algorithm. Okay. So, that we have to be more cautious about. So, here initially I need 3, but here I need, sorry, here I was needing 4 for this 8 bit operation, but here I need 3 stage. That means only one stage I am just reducing. Apart from that, what? But I am increasing the complexity of the Booths decoding algorithm as I have used Radix-8 over here. So, that thing we have to be careful that whether we are increasing, or it is not meant that all the time if I increase the radix it will give me the advantage. Okay. So, that should be whenever you are designing. So, at that time you should be more careful that for what purposes, for what number of bits you are considering. So, at that time whenever you are considering those number of that means the bits for those multiplication. So, at that time what radix, if you choose Radix-8, at that time does it giving you the benefit or it is not. If it is giving you the benefit, so at that time you can go ahead, otherwise you have to be satisfied with the lower radix. Okay. So, this is the main fundamentals of Booths decoding technique. Okay. Now, again just here whenever we are doing this Booths decoding, so at that time what I said, if I choose Radix-8, so at that time the shifting, that means this is the first partial product generator, then the next partial product generator, that will be added by shifting of 2 bit, as you have chosen the radix of 4. So, that means the next again that is 2 bit. In generic multiplier what we do? We shift only 1 bit, but here 2 bit. If we choose Radix-4 8, so at the time 3 bit shift will be there. Okay. But what about this particular, that means positions? Okay. So, this particular position, if I filled all this with 0, at that time for the sign value, the corresponding results which I will get, that will be total erroneous results I will get. So, that is why I need the sign extension of that. Why I need this sign extension? Because in the decoding table what I find that, okay, sometimes I need 2 of minus a, minus 2 of a, or minus of a, means what? This is nothing but the 2's complement. So, minus of a means 2's complement means this sign, that means the MSB, that has to be extended up to the that means maximum MSB site. That means whatever the bit position is this, so that will be copied multiple times for this particular position. So, this is for the next set, whatever is the bit position over here or MSB of this, that will be copied for this, whatever is this the bit of this, that will be copied to this 2 bit position. Okay. And then you do the Wallace tree multiplication, that means what Wallace tree structure, that means then Wallace tree structure means you just add something like this, or using carry save adder or using carry look adder, sorry. So, using any of this, now you can just do this addition operation. Okay. So, that means what, if I use generic carry save, that means Wallace tree multiplier, at that time this depth I need is more than, here I need 4, but if I use only Wallace tree, so at that time I need 8 stages. Okay. So, this is the sign extension method which I need to follow whenever we are using this Booth multiplier architecture. Okay. So, if we take one example or using, that means how we perform this sign extension whenever we are using this Booth's algorithm. Suppose this is the that means the multiplicand and this is the multiplier. Okay. So, this value is plus 3 and this value is plus 29. So, the results which will be plus 87, right. So, what I need to do? I need to add 0. So, then for 0 1 0, so the case will be plus 1, for 0 1 0 that is plus 1. For 1 1 0, for 1 1 0 the case is minus 1. Then again for 0 1 1, that means the corresponding decoding table says that the multiplicand will be plus 2. So, that means now for positive of A, then that I have to write, for positive of A I have to write something like this 1 2 3 4 then 1, and for as this is 6 to 6 multiplication. So, that means total 8 bit will be there. So, that means the rest of the 6 bit position all will be filled with 0 as this bit is 0 over here. For negative of this will be what, 2's complement of this number. So, and that will be 2 bit shifted. So, 2's complement of this number is 1, then that is 0, then all 1. But as this bit is 1, so that means all the 1 will be shifted to the corresponding MSB site. Then this is for plus 2. So, it will be started from this particular case, and plus 2 means that means 1 0 has been padded at the LSB position. Okay. Basically plus 2 means multiplying with 2A means 0, if I add 0, so that becomes 2A. Okay. So, 0 that is added to this, and then again that MSB is shifted to the MSB side. Now, I need to add. So, this is 1, this is 1, this is 1, then this position is 0, this position is 1, this position is for 1 1, this is 0, for 1 1 this is 1, for this is 0, for this is 0, this is 0, this is 0, this is 0, this is 1. Okay. So, this carry will be discarded. So, as this all this position that means the MSB of this is 0. So, this is one positive number. Okay. And what is the magnitude of this? The magnitude of this is 1 plus 2 plus 4 plus 16 plus 64, that is equals to 87. Okay. So, the result is 87 plus So, plus 87 is the results I am getting using Booth's multiplier or Booth's algorithm. Okay. Then you that means next, if we change the number, that means plus 3 to minus 29 or any of this number to minus. So, at the time what will happen? Okay. So, at the time what will happen? Here you see I have changed the number to these two minus 3. So, minus 3 means 2's complement of that. So, as this is 0, at this bit is remains unchanged. So, that means that corresponding decoding will remain same. So, decoding will remain same means for minus 3, as this bit is 1. So, that has been extended up to this. So, in the previous case, as this bit was 0, so 0 was extended, but as in this case 1 is there, so 1 is extended, and for minus 1, 2's complement of this, that will be this. So, that means as 0, so 0 is extended at this particular position. So, again for this case plus 2 means, so 0 is padded, and apart from that all are, the 1 is extended because this is minus 1 now. Now, if I just add, so at that time what will happen? 1 for this, 0 for this, for 1 1 0, okay, and 1 carry 1 comes over here. So, this is for 1, then 1 over here, for this is for 0, then 1 1 1, this will be 1, then 1 1 there 0. So, 1 1 1 1 1 1 1 1 all 1. So, this 1 means, okay, if I just discard the that means outer carry. So, the MSB is 1 means this indicates this is the negative number which remains in 2's complement format. Okay. So, this is negative, and if I take the 2's complement of this, then this will become 1 0 1 0 1 all 0. So, this indicates this is the sign which is negative, and the magnitude is this, which is nothing but the 87. Okay. So, that means using the sign extension I am getting the corresponding results of this. Now, suppose if I do not use this sign extension, at that time what will happen? If I do not consider this particular bits, so at that time what will happen? Can I get this minus 87? If I check that, so at that time if I do not consider this, so at that time what will happen? 0 1, okay. For this case this is 1 1 0 0, and for this case what is that? That means value is 0 1 0 1 1 1 1, okay. Sorry, 1 1, and then this is all 0, okay. So, now if I just want to add 1, then 0, this is 0, this is 1, then this is again this is 0, this is 1, this is 1, and then all 1. So, as this bit is 1, this indicates negative, okay, very fine. But what about this magnitude of this? So, this is 1 1 1 0 1, then all 0 I am getting. So, is it the number 87? No. That means I am not getting the corresponding values of this 87. The magnitude is totally different from this. That means I am getting the results, erroneous results, if I do not extend this sign at the MSB position. Okay. So, then again if I consider another example of this, where I am both the numbers are different, that means negative. So, at the time at the results what I need? I will get positive value, right. So, again here you see this will change. So, at that time, so negative of that means now the corresponding these two position will be. So, initially this was 1, this was 2, this was minus 1. Now, this one will be minus plus 1, this 2 will be minus 1, sorry minus 1, this will be minus 2. So, now based on that, if you just do, you will get plus 87, because you are getting 0 over here. Okay. So, this is the sign extension. Then what is the problem here? Is there any problem? Yes, obviously there is a problem. As I am increasing the sign bit over here, as I am increasing the sign bit for this particular partial products, that means I am increasing the full adder cell, that whenever I will use this to add these particular bits using Wallace tree or any other addition operation. So, at the time I am using the competition. As I am increasing this, I am putting this value extra bits. So, that means I am increasing the complexity of the circuit. Okay. So, is there any way out to reduce that? Can I reduce that? Okay. So, that this is regular shift, and basically this is regular shift, and this is this Booth's multiplication. Can I do that? Yes, I can do that. I can reduce the sign extension for Booth's algorithm using this template. So, what type of template? We will see that. Suppose this is the first set, and then this is, that means the partial products are something like generated something like this. So, then it says that, please note that each operand is, this is considering 8 cross 8. So, 16 bit is 17 bit, that is the 17 bit is the sign bit. Also, negative numbers are entered as 1's complement. This is why you need to add the s in the right hand side of the diagram. If you use 2's complement, then the s on the right hand side of the diagram can be removed. Okay. So, this is the, that means instead of putting this s up to this position, I can write something like this, so that I can remove the extra burden of extending the sign up to this particular position. So, how we can do, or what is the logic behind to putting that means this 1 and s bar, what is the logic behind that? We will take the example, and then we will see how we can do that, or what is the, it is not that from the air it is coming, there is a logic behind it. Okay. So, that we will see in the next class, we will discuss on that, how we can using this sign extension. So, means what? Actually what I need to do, that means I need to reduce this extra overhead which are required for, if I have not used this kind of notation, I have to extend the sign, that means for this particular position which will be filled with redundant number. So, to remove those, I need these techniques which will be, I will be discussing in the next class. Okay. So, thank you for today.